Assalamualaikum warahmatullahi wabarakatuh. My name is Adi Amzi bin Adidi, and today for the second part in the generic skill of semiconductor PW3, and then I want to show you how to do the application of diode in half wave rectifier. So the circuit I have been set up is this is the diode, and then this is the resistor. And then we are using the function generator and also the oscilloscope. Both of this machine have been calibrated by me, by myself. And also we are going to proceed to the process. First, by using the PW2 practical work 2, we need to use the function generator to connect to the circuit. So we are doing like this. Okay, and then for the oscilloscope, the channel 1, we will connect this at the same place for the supply. But for the channel 2, we are going to connect this at the resistor. Okay, so this is the circuit that we will need to experiment. And so, if you want to measure the input and output, we just turn on both of this machine. Wait for a minute to get the result. And so as you can see, this is the result. For the full cycle of the rectifier, this is the input. And also for this is the output. Why it has been half is because that's why it's called the half wave rectifier. So for the second part, I have done this part in the lab by myself, and also for the next part, I will explain deeper about the half wave rectifier in a diagram. So that's all from me for the second part.
Welcome to our channel. Today we will see how to convert AC to DC. There are two main types of electrical currents commonly used: alternating current AC and direct current DC. AC constantly changes direction while DC flows in only one direction. In our houses, we receive AC from the power grid, but most electronic devices require DC. Therefore, we need to convert AC to DC through a process called rectification. An electronic circuit that rectifies AC into DC is called a rectifier. A rectifier consists of diodes. A diode is a semiconductor device that allows current to flow through it in only one direction. For example, if we connect a lamp to a DC power supply, it will illuminate. We can reverse the leads, and it will still illuminate. However, if we add a diode in series with the lamp, it will illuminate again, but if we reverse the leads, the diode blocks the current and the lamp remains off. Now let's discuss the rectifier circuits. First, the half-wave rectifier circuit. In this circuit, we first use a step-down transformer to decrease the voltage from 120 or 230 volts AC to 12 volts AC. Then we convert this lower voltage to DC using a diode. Only one diode is connected in series with the load in this circuit. This diode allows current to flow in one direction, resulting in a pulsating waveform, because it only rectifies the positive half of the AC sine wave and blocks the negative half. Therefore, it's called a half-wave rectifier. The output is technically DC because the current doesn't change its direction. We can improve the output by adding a capacitor in parallel with the load. Next, the full-wave rectifier circuit. There are two types, the 2-diode circuit and the 4-diode bridge circuit. Unlike the half-wave rectifier, the full-wave rectifier rectifies both the positive and negative halves of the AC sine wave. This results in a smoother output compared to the pulsating waveform of the half-wave rectifier. In a full-wave rectifier, 2 diodes are used and a center-tap transformer. A center-tap transformer simply has another wire on the secondary side, which is connected to the center of the transformer coil. This allows us to use the full length of the transformer coil, or just half of it. During the positive half cycle of AC, the current flows from the top end of the secondary winding through the diode and the lamp and returns to the center tap of the transformer while the other diode is reverse biased and blocking the current. And during the negative half cycle, the current flows from the bottom end of the secondary winding through to the diode, and the lamp, and returns to the center tap of the transformer. This arrangement ensures that current flows through the load in the same direction during both halves of the AC cycle, effectively converting AC to DC. Now, let's see the most commonly used full bridge rectifier. But before we continue, if you're enjoying this video, please ensure to like and subscribe to the channel. A bridge rectifier circuit consists of 4 diodes arranged in a bridge configuration. Let's see how it works. During the positive half cycle of the AC input voltage, the diodes D1 and D2 are forward biased, conducting, while diodes D3 and D4 are reverse biased, non-conducting. This allows current to flow through the load in one direction, from the transformer to the load. During the negative half cycle of the AC input voltage, the diodes D3 and D4 become forward biased, while D1 and D2 become reverse biased. Again, current flows through the load in the same direction from the transformer to the load. As a result of this process, the output voltage across the load is always positive with respect to the ground, effectively converting the AC input into a pulsating DC output. To smooth out the pulsating DC voltage, a capacitor is often connected across the load, which helps to reduce the ripple voltage, resulting in a more stable DC output. Both types of full-wave rectifier circuits offer advantages over the half-wave rectifier, including higher efficiency and smoother DC output. To summarize, rectifier circuits are essential for converting AC to DC. The half-wave rectifier rectifies only the positive half of the AC sine wave, while the full-wave rectifier rectifies both halves, resulting in a smoother DC output. These circuits enable us to power electronic devices that require a stable DC supply. I hope you found this explanation helpful. Don't forget to like and subscribe to the channel. Thank you.